Hello and welcome to the Astro Podcast. Today I'm your host, Oindrila Majumdar, and today we are thrilled to be joined by Ava Polzin, a PhD candidate in Astronomy and Astrophysics at the University of Chicago. Her research delves into galaxy evolution, focusing on star formation and their baryon cycle in low mass and low metallicity galaxies, which we'll be exploring in depth today. But beyond her research, she's also deeply interested in STEM outreach programs, working to make astronomy more accessible to diverse communities. Welcome, Ava, to the Astro Podcast. Is there anything you'd like to say before we get started?
I think just thanks for having me, and yeah, thrilled to talk about some of this. Hopefully it's interesting to your listeners.
Of course. So how this podcast will go today is that we have four main topics that we'll be covering today. And the first one, which is on the universal star formation, efficiency, and turbulence, which are two new terms that you might be hearing about. Like, how do galaxies have turbulence? What does that really mean? And we'll be really exploring how star formation maintains a surprisingly consistent efficiency across all galaxies. And your research obviously reveals how turbulence and stellar feedback help us regulate these processes in galaxies. So before we start, could you give us a brief overview of, what turbulence and efficiency means in galaxies?
Yeah, so turbulence, you can think of basically the random motions in these galaxies and the gas of these galaxies. So often when we think of galaxies, we're thinking about the stars in them. That's, the stellar component that we're most familiar with, just because when we actually see pictures, that's mostly what we're seeing. We're seeing what we'd call stellar light. And so that's from the stars directly, but equivalent to that mass in galaxies, sometimes even greater than that mass in galaxies, is this gaseous component. And that's functionally how much gas there is in the galaxy. Now, that's not the kind of gas you're thinking of when you're doing like a chemistry lab. This is actually generally hot and dense, but because it's relatively diffuse compared to, our environment here, if you were to go out in space in the interstellar medium, you wouldn't feel anything. Like, you wouldn't feel that it's hot because the actual particle density is very low. But for astrophysically, these are very dense clumps of gas, and of course they can get even denser and eventually coalesce to form stars, and that's why they become very, very dense. When we're thinking about that turbulence, that's random motion in the gas that can be injected from various sources, from the winds of young stars, from supernovae, from all sorts of different things. But we actually don't fully understand where it comes from, and we don't fully understand how turbulence behaves in these galaxies. So this is an active area of study. And then to your question about star formation efficiency, so when we're talking about the efficiency of star formation, there are actually two different terms. It's the same term, but it's used two different ways depending upon who you're talking to in the context. So there's this idea of star formation efficiency, which is per unit mass in the galaxy, how much of that mass is in stars. So per like halo mass or per gas mass for the entire galaxy, how much of that mass is stars. And that is this kind of global term that we think about with respect to galaxies in different sort of mass bins. And this tells us something about the processes that are in play for each of them. But when we're talking about star formation efficiency on the scale of an individual galaxy, and that's what we're talking about here, what we're thinking about is how much of the gas is converted into stars over, in this case, a free fall time, which is basically just a uniform time scale that's dependent upon the density of that gas. And so when we're talking about star formation efficiency this way, this uniform star formation efficiency, what we're thinking about is in self-similar gas. So that is to say, gas that has basically a particular density or across densities, but it's normalized by this free fall time, which is density dependent. How much of that gas, what percentage of that gas, what fraction of that gas is converted into stars? Most galaxies we find, both empirically and from simulations, have star formation efficiencies per free fall time. And when I say star formation efficiency, I'll just be talking about this kind of like smaller scale property. Most galaxies have that at about the percent level. And that's very interesting because these galaxies have very different chemical properties. So that was, what you're mentioning with metallicity, right? That's like the chemistry of the galaxy. They have very different densities. They have very different environments that they live in. Some of them are isolated. Some of them are in crowded environments where they have these interactions with massive neighbors. Some of them have very different feedback processes happening in them. Some have supermassive black holes, others don't. Some have young stars that are impacting them. All of this is kind of going into each of these galaxies, and there are obviously many more properties that I haven't discussed. But despite that, we find empirically and in simulations that all galaxies pretty much have a star formation efficiency of around 1%. And I say around because it's, on order of, it might be 2, it might be 3, it might be 0.5%, but it's around 1%. And the scatter in this is driven generally by the time scale in which you're actually observing this. In simulations, we observe it instantaneously. But observationally, we're actually seeing gas in all different sort of states, and in all different kind of parts of their little evolution as a gas clump. But overall, it's this kind of 1%. You can think of 1% of gas forming stars over this very particular timescale that we think about in galaxies.
So you're saying that efficiency and turbulence have a lot to do with the chemical properties of the galaxies, and I also know that your work revolves around dwarf galaxies, much smaller galaxies. So my other question was, obviously dwarf galaxies have a different composition than a much normal sized galaxy that maybe we live in, or the Andromeda galaxy right next to us. So how do these different gases, form? Was it during the Big Bang or after the Big Bang, or was it because different galaxies collided to form these small galaxies, or how so did these happen?
Yeah, so we can think of the early stages of galaxy evolution basically happening the same way in all cases. So in the very early universe, and we were thinking around redshift 30, we're starting to get up here with JWST, and so we'll probably have even better constraints than just the theory soon. But around redshift 30, so this is very, very quickly after the Big Bang, we have basically seeded overdensities in the sort of just general makeup of the universe. And those overdensities are generally in dark matter or just in mass in general, and they give rise to the growth of large-scale structure. Now, that's just because we have what we think of as hierarchical growth. So basically, big things get bigger, and they get bigger by merging things that are smaller, that are nearby, and so on and so forth. It's just an effect of gravity. And so all galaxies sort of form out of these small clumps that eventually get bigger over time. And what's interesting about dwarf galaxies is they should be the most abundant galaxies in the early universe and now. So they've been the most abundant this whole time. But in the early universe, they were pretty much the only galaxies. And so when we think about local dwarf galaxies, and when we're talking about local, we're talking about within 60 million light years. That's generally where I work. I mean, sometimes it's out to 120 million light years, but generally kind of in this regime, or in megaparsecs. For your more informed audience members, we're thinking 20 to 40 megaparsecs. This is kind of the distance out to which we can see these low mass dwarf galaxies consistently at this point. And when we're observing them, we're actually observing something that should be very similar in chemical composition, in density maybe, although that one's a little bit more of a question mark, and in physical condition to galaxies in the early universe. So we can think of these things actually as local analogs of high redshift galaxies. Now that's very interesting because, of course, this primordial chemistry is very much something that we're studying now at high redshift with JWST, but those galaxies are so distant that we can't study them in as much detail. So we're studying them currently, locally, as dwarf galaxies, and we're thinking that these are analogs of these high redshift galaxies that we're seeing. And what that actually can tell us is detailed information about those processes. Now, you asked about how similar dwarf galaxies are, or kind of putting it in context. As these sort of halos coalesce into bigger and bigger galaxies over time, they have more generations of stars. So we think about the gas originally that's in these halos. And I'll use halo as a generic term because, at what point do they become galaxies? It's a bit of a question. But in these halos initially, we think we have what we call pristine gas. So it's just hydrogen, maybe a little bit of helium, but it's pretty much not chemically enriched. So we don't have any metals in there. And your chemists in the audience will be horrified, but everything heavier than helium for astronomers is a metal. And so we don't have any metals in the very, very, very early universe. And the stars that form out of that very primordial, pristine medium, we call POP3 stars, population 3 stars, which is just because they're coming from this entirely hydrogen-based gas. Over time, though, generations of stars, when they explode because of fusion in their cores, so stars when they fuse are actually creating new and heavier elements in their cores. And when massive stars die, when they reach the end of their lifespan, they explode. And about 50% of that material is returned into the interstellar medium, so into this gaseous medium in the galaxy. And that means that over generations of stars, we have chemical enrichment. So as you have more generations of stars, you get more chemical enrichment. And for more massive galaxies, unlike dwarf galaxies, because they're so massive, they actually can really hold on to that material that's in them. With low mass galaxies, with dwarf galaxies, for instance, we actually think supernovae, when they happen, can blow material completely out of the galaxy because the potential well, the gravitational potential of that galaxy is insufficient to hold on to that material. And so you have kind of two effects leading to these galaxies, local dwarf galaxies, being chemically unenriched compared to more massive galaxies. Basically fewer opportunities to even have these massive stars explode and return any kind of material to the interstellar medium. And simultaneously, when these stars are exploding and returning material to the interstellar medium, they're actually doing it in such a violent and energetic way that it's blowing that material out of the galaxy, just clear out of the galaxy. And so these dwarf galaxies are in fact chemically unenriched, which is very interesting because again, they're like the primordial universe. But they also are really interesting for these sites of feedback. So just to introduce that idea very briefly, when we're talking about these supernova explosions being so energetic that they're blowing all of the gas out of, not all, but quite a bit of the gas out of the galaxy, that's what we're talking about when we're saying feedback. These are the things that regulate star formation. And because they're so low mass, that feedback is more effective in them, and it makes them a very interesting site to study that kind of stuff.
So it's quite interesting that, dwarf galaxies are, not as chemically enriched. But if dwarf galaxies aren't, as enriched with chemical elements, then I think will there be less activity that happens in the galaxies? Like in normal galaxies, we know that they can host black holes. They can like black holes in the middle of in the center of the galaxies, and they can also create nebulas, which host small stars, like baby stars that are being born. So does that mean in low dwarf galaxies they can't really produce these types of phenomena because they're not as chemically enriched as normal galaxies?
No, it doesn't. So, in fact, all of those things can happen in any sort of gas. Generally speaking, when we're thinking about dwarf galaxies, yes, we don't think that they have as many massive black holes as we see in more massive galaxies. So, I guess for some reference, dwarf galaxies are the most abundant galaxies in the entire universe. So, when we talk about normal galaxies, we actually should be talking about dwarf galaxies. This is something in the last 30 years that we haven't really started doing yet because it's just been, again, like 3 decades where we've been able to study these at the population level because they're small and so they're kind of faint and they're hard to observe out to great distances. But overall, dwarf galaxies are something like the typical galaxy in the universe if you were to do an average by mass. And so it's like imperative that we understand these things, right? Like they're not a novelty item, I guess, in the way that some people might think just because they're small. And so it's really key that we understand what's going on in them. And again, it's only been very recently that we've understood very much about them at all, again, on the scale of decades. So for reference, until fairly recently, we didn't really think that low-mass galaxies could host supermassive black holes, but we've been finding them recently. This is not something that I personally work on, but various teams and some people that I know have been finding them recently, and they're quite abundant. So down to even 10 million solar masses. So typical dwarf galaxies are roughly, and the people who work on ultra-faint dwarf galaxies, which are between, let's say, 10 and 10,000 or 100,000 solar masses, are going to be frustrated with my definition. But typically dwarf galaxies, when we think about them, are between roughly 1 million and 1 billion solar masses. So we use the mass of the sun as sort of an indicator of how massive things are. Galaxies like our Milky Way are orders of magnitude more massive than that, but roughly, million to billion solar masses for classical dwarf galaxies. Ultra-faint galaxies, which again, I don't work on and so I won't focus on, but those are somewhere between 10 and 100,000 solar masses. So they're very, very small, some of these galaxies. In the classical dwarf regime, though, we have started seeing supermassive black holes. So in the 10 billion to about 100 million solar mass regime, we didn't previously think that we could see black holes there, but there are now catalogs that include many such galaxies that have massive black holes detected in various different ways. And so we know empirically that we can see that. We previously didn't think that that was necessarily possible just because of the way that supermassive black holes form. But that is something that we're seeing. Simultaneously, we certainly see nebulae in these low mass galaxies. In fact, there's some very pretty examples. So when we're thinking of the pretty pictures of nebulae, you're really just looking at ionized gas. So that can be ionized from the actual behavior of young massive stars. And we think, this is a bit in question, but we have what we call the initial mass function. So basically, when a population of stars springs out of a giant molecular cloud or a cloud of cold gas, how do those stars form? What is the distribution of stars in bins of mass that form? And we have the IMF, which is sort of a panacea insofar as people like to tweak it to explain various things. But our understanding of the IMF is basically that it should be pretty much the same. And I say pretty much because, again, people do tweak it a bit in different directions and it may be a little bit different. But it's pretty much the same whether you're looking at a low mass small galaxy or a large galaxy like our Milky Way or something even larger. The real differences come from the fact that for small galaxies, you're stochastically sampling the IMF. And so it's not that it's an intrinsically different distribution of stars, it's just how well sampled that distribution of stars can change. But it's getting a little afield. And so if people are interested, look up the IMF or the initial mass function. But no, generally speaking, we expect that dwarf galaxies in general have all of the same physical processes that we see in more massive galaxies. There are just some differences. For instance, gas cools less efficiently when it's not metal enriched. So we have what's called metal line cooling, and that's the most efficient form of cooling. Now, as soon as you have any metals in the system, and you do have some metals in the system for dwarf galaxies, this goes into effect, but the cooling is less efficient than you have in more massive, more metal-enriched galaxies. And that leads to differences in the proportion of gas that can actually form stars, for instance. But it doesn't change the actual functional behavior of the star formation the same way that you might think, given that it's all a chemical process.
That's pretty interesting to think about since they're not as chemically enriched as normal, galaxies that exist in our universe. And I wanted to know, I think we had discussed a little bit in our brief meeting a few weeks ago, more on the environment of these dwarf galaxies and how they can affect it. So I wanted to know a little bit about that as well, what kind of surroundings are you talking about, or how these surroundings or environment of these dwarf galaxies can really affect it. Because, for example, if there's a large galaxy near a dwarf galaxy, obviously, the gravitational force can, cause them to collide, and many more situations exist, in our universe or in the cosmic web. So that's my question.
Yeah. So in general, when we're thinking about the environments of galaxies, they're kind of, as always, there are multiple things we could think about. So probably the most interesting to think about is the gaseous environment of these galaxies. It's called the circumgalactic medium, and this is also something that I work on, but those papers aren't out yet, so I won't go into detail there. But when we're thinking about the CGM of low mass galaxies, that's not very well studied, and this is something that we're increasingly studied. So, people who are interested should keep an eye out for some of my forthcoming work on this. But I think your question is more related to the kind of neighborhood, let's say, that these galaxies are in. So when we're thinking about dwarf galaxies in particular, we can think about them as kind of two different classes of object. So there are isolated dwarf galaxies. So those have no nearby neighbors. And some people define that as no nearby massive neighbors. Personally, I care if they're in dwarf groups because any kind of interactions can impact what's going on with them. But they also can be satellite galaxies. Now, you could make the argument that some of them could be what we would call a central galaxy. So that's the most important galaxy in a group. And then the other galaxies are the satellites of the central. But generally speaking, when we're looking at dwarf galaxies, we're looking at them in what we call the local group. So that's the supergroup between Andromeda and the Milky Way. And most galaxies that we're looking at, most dwarf galaxies, are satellites of those two systems. So I'm interested in dwarf galaxies outside of the local group. So that's, again, outside of this kind of 3 megaparsec box. And that's because those galaxies can be in all sorts of different environments. When they're very local, when they're near to massive galaxies, those massive galaxies can siphon off gas from them. It can heat gas dynamically due to interactions. It can disrupt the galaxy and remove the gaseous halo entirely. It can starve the galaxy. We call it starvation because the galaxies can't actually accrete more well, I shouldn't say more. Sometimes any can't accrete any gas from the CGM. It's all being accreted onto the more massive galaxy nearby. And so there are all of these different kind of dynamical things that can happen just because more massive galaxies, larger potential, well, they are actually able to pull in this material, whether from the smaller galaxy or from the surroundings, and then prevent the small galaxy from getting that material. But yes, as you said, you can also have mergers. And so if a dwarf galaxy, for instance, merges with a more massive galaxy, we don't actually call it a merger at that point. We think of the dwarf galaxy just being accreted onto the more massive galaxy. And that's how we think, for instance, the halo of our Milky Way built up, was generations of dwarf galaxies being accreted onto the halo and being basically stripped apart and stripped for parts insofar as their stars become the halo stars. And we also see this now with stellar streams, which are a huge area of interest, where we think that these stellar streams, you can actually reconstruct which dwarf galaxies they came from, because we think that that's also how those came about. And so there are all sorts of horrible things that can happen to little galaxies when they're in the presence of big galaxies. When they're in what we would call a dwarf group, or a dwarf-dwarf group, depending upon how many galaxies there are in this group, but if it's in a small kind of pod of other dwarf galaxies, then you get into more interesting, like you can have major mergers, which is what we call it when the two galaxies that are merging have approximately the same mass. So you can have major mergers between those. Those are very disruptive. They don't actually damage the galaxy per se, but they will merge fully, and it will be very disrupted as a system. It'll be very heated as a system. It'll be, kind of not a good place for stars to form for a while. And you can also get these interesting effects where if you have two dwarf galaxies near each other, and there's a great paper out recently by Aaron Cato-Fogg on this, one dwarf galaxy may actually have enhanced star formation due to this interaction, while another one may be quenched or not forming stars anymore. And so there are all of these funky things that can happen when you have similarly sized galaxies near each other. And then my favorite class of dwarf galaxies are isolated dwarf galaxies, which are totally alone in the universe. We call them field galaxies. So they're far away from any massive neighbors. And again, I would say far away from other dwarf galaxies. And those are so fun because we know that whatever's happening to them is happening due to the internal physics. We don't have to worry about what the environment is doing to them. We can just think about what's happening internally. And of course, people have posited that maybe some of those isolated galaxies actually were near a group before and are now isolated, or have had interactions with the cosmic web or with other large-scale structure that are actually suppressing star formation or impacting their behavior. But sometimes we can tell and sometimes we can't. And so often when we're looking for these isolated galaxies, we're trying to rule out these other scenarios just to make sure that what we're actually looking at is internal feedback. So what is happening in the galaxy physically and chemically that is either promoting or halting star formation? And we think that these field dwarfs are particularly interesting for that. So that's my plug for we should all care about isolated dwarf galaxies, but they're also the hardest ones to find. Often people are finding dwarf galaxies because they're satellites of more massive galaxies, and they're already looking at that galaxy, that massive galaxy, and they're looking around it to see what exists. But these field dwarfs have to be found generally fairly serendipitously, and we're generally looking for them well outside of the local group environment, which means that they're more distant, and if they're small enough to be interesting, then they're generally very faint. So it's a challenge, but it's something that we really need to invest in. So if anyone is on this call who's a funder for NASA or NSF, just keep that in mind.
No, I think this term that you guys are using, starvation, like starving galaxy, because rather they're not accreting any, but they're actually just the food for a bigger galaxy that they're feeding, that is feeding off them. And then I think it's really interesting to think about that most of our galaxies in our universe are just are just formed from these dwarf galaxies from the beginning of our universe. And then about the isolated galaxies, I think that eventually all galaxies will just become isolated because as our universe is expanding, obviously all galaxies are moving further and further away from each other, and then eventually everything will just get dark and all galaxies will be isolated, which is pretty sad at the end.
Yeah, I think there is an argument to be made that at some point in the very distant future, in groups, all galaxies will have merged into what we call a CD galaxy, a cluster dominant galaxy, and all other galaxies will have been flung far afield, and so there will be nothing near each other. But don't worry, that is so many billions of years in the future. I don't think you need to worry about it. Right now is a point of sadness, if that makes you feel at all better.
Because I think we should finally start with our topic two, which is actually about the baryon cycle and galaxies. This is something I actually really want to talk about because the baryon cycle is kind of about like the inflow and outflow of galaxies. And I know that your work on low mass dwarf galaxies explores why some galaxies, despite even being enriched with gas, show that low star formation rates happen, which is also something which is called quenching, I'm sure. So maybe if you can explain, what the baryon cycle is and how that kind of impacts galaxies formations.
Yeah, so I guess I'll start with what are baryons, which I know, again, the particle physicists will hate us for this, but when we refer to baryons in astrophysics, we're thinking about only, normal matter. Now, technically, not all normal matter is baryonic, but we'll leave that be for the moment, and we'll just say, baryons as a generic kind of colloquial astrophysics term is anything that's not dark matter. That's really what we mean when we say that. So the baryonic components of a galaxy are like stars and gas and dust, and also, their surrounding environments, of course. And so when we're thinking about the baryon cycle, we're thinking about the fact that cold gas, or gas as it cools and becomes cold, coalesces to form stars. Those stars at the end stages of their stellar evolution can explode, returning gas to the interstellar medium or blowing gas out of the system. It also heats gas and ionizes gas. Gas can be reaccreted from the surroundings or blown into the surroundings, again, by these different sort of processes. And that gas, when it cools down again, forms stars again, and you get this basically life cycle, not of stars, but of all of the kind of baryonic components of a galaxy. Now, when we're thinking about that, we're also thinking about the fact that the baryon cycle is not uncomplicated. There are many different things that can happen. So fundamentally, the conditions necessary for stars to form are gas needs to be cold and dense and neutral. When we're thinking about the things that can disrupt this can be gas being heated, ionized, or physically disrupted, dynamically disrupted, kinematically disrupted. And again, that can happen a myriad of ways. So we've already talked about what happens when they have massive neighbors. Supernovae can impact this gas by having both energy and momentum injection, so dynamical impacts, and then also the fact that you have this energetic injection that can ionize gas and heat gas. Simultaneously, young massive stars, in dwarf galaxies in particular, are sufficiently hot and sufficiently radiative, let's say, to ionize and heat the gas around them. So we think on all galaxies, there's a decorrelation between recent patches of star formation and patches of ongoing star formation, a spatial decorrelation. And that's just because of this kind of disruptive nature. But in dwarf galaxies, which are small, sometimes one patch of star formation is all it takes to actually completely halt star formation in the entire galaxy. And so this is what we'd call stellar feedback. Now, all of these different processes, again, are coming from heating, ionizing, physically disrupting the gas. And so all of the time when we're talking about stars forming, we're thinking about the things that will get the gas to be cold, neutral, and dense. Now, classically, the picture of that is cold, dense gas forms into a molecular phase prior to forming stars. But molecular hydrogen is actually very difficult to form in low metallicity gas. And this is just because it needs to be sufficiently cool for it to actually have molecular hydrogen form. The timescale on which that cooling occurs is often as long as the lifetime of these star-forming gaseous clouds. And so what that means is for very, very low mass, very low metallicity galaxies, we actually think that maybe there's the chance that star formation is happening not preferentially in, but just is happening in atomic gas. And that's very interesting. That's an alternative star formation pathway for low metallicity galaxies. Obviously, if molecular hydrogen is present, that will be the kind of preferential reservoir of star formation. But we think, and we found this in simulations that I've worked with, we found this in other simulations, people have even kind of found it empirically, because there's indication that you have these low metallicity galaxies that are forming stars, that you don't necessarily need molecular hydrogen where it's not forming. And that means that across all galaxies, of course, atomic hydrogen can also form dwarf galaxies. Oh my gosh, form stars. Talk about dwarf galaxies way too much. And as you're forming stars, that process really shouldn't change. So we think self-similar patches of gas, whether in a local dwarf galaxy, a galaxy at high redshift, a massive galaxy here or at high redshift, we think all of those should form things basically the same way. It's just that the majority of star formation in a more massive, more metal-enriched galaxy will come out of molecular hydrogen. But that's not to say that all star formation has to happen that way. So that's one little tweak, let's say, to the baryon cycle as we understand it. We also need to understand how energetic are supernovae, or are these various processes that are removing gas from the system. How much of an impact does the radiation field from young massive stars have? When gas is cooling, are there other things that can impact it? Can, dynamical disruption, like from turbulence, both disrupt star forming regions and also have this compressive force that can promote star formation elsewhere? So these are all open questions, and this is something that we really need to work out. People want to use galaxies for all sorts of other cosmological projects even. So a lot of people are very interested, what is the mass profile of a dwarf galaxy? What can that tell us about the underlying dark matter halo? Because these things should be dark matter dominated. So the shape of this profile should tell you something about the shape of the underlying dark matter halo. That's great and all, but we don't understand what's happening in the galaxy to actually cause that mass profile in the baryonic matter that we can trace. And what that means is that if we're thinking about transforming a light profile that traces baryonic matter into a mass profile that traces all mass, really it's tracing baryonic mass, but we think that that should follow the dark matter profile, we need to understand what's going on with feedback, because that feedback is actually what's impacting the shape of that light profile and the baryonic mass profile. So that's one sort of point of import that I often have to say to my dark matter colleagues is well, actually, we should care about my stuff. Intrinsically, though, we also want to understand how generations of stars like our sun formed in galaxies like our Milky Way. And to do that, we have to understand star formation in low-mass galaxies, because these low-mass galaxies are the progenitors, or analogs for the progenitors, of modern-day massive galaxies like our Milky Way. And so, intrinsically, even from kind of a human standpoint, we want to know where we came from. And understanding these dwarf galaxies helps us understand what conditions gave rise to Earth, among other things.
Wow, that's a lot to take in as well. But I wanted to go back to one thing you had said before. I feel like the baryon cycle kind of explains how matter gets, recycled in a galaxy. But you had said that don't you think that, heating or ionizing the galaxies or the dwarf galaxies can maybe change the composition of these galaxies? Kind of, or would it just make it more active?
Yeah, so this occurs in all galaxies. I focus on dwarf galaxies because they are most susceptible to some of these processes, particularly from young stars. But when we're thinking about ionizing, yes, absolutely it changes the composition. So for instance, we go from what we call H1, which is neutral atomic hydrogen, to H2, not H sub 2, molecular hydrogen, but H, like 2 little Roman numerals, which is singly ionized hydrogen, or just ionized hydrogen. And that H2, when you see those kind of colorful patches when you're looking at a galaxy image, those are usually H2 regions. And those H2 regions are due to ionization from young massive stars. So if you've ever seen a picture of a galaxy and there are these bright blue patches, and they're like kind of, neon isn't quite the right word, but they're very, very blue, and they're like an electric blue, let's say. Those are usually H2, again, small Roman numerals, 2 regions, which is ionized hydrogen. So it does fundamentally change the composition. Now, it doesn't generally change the composition on a sufficient scale for us to consider the galaxy primarily ionized. In fact, we generally assume that this ionized component is negligible with respect to the atomic and molecular phases of gas. And we think that pretty much across the board. Ionization is hard to kind of reach. But we have other lines, so like the O3 line, for instance, so that's doubly ionized oxygen. So again, three little Roman numerals that we use to trace ionization, because it's not just hydrogen. We tend to care about hydrogen because it's the most abundant element in the universe, and also we think for particularly galaxies here and now, still, we're forming stars out of hydrogen gas, although it's polluted hydrogen gas, so there are other elements mixed in there, but it's generally hydrogen gas. In the early universe, we're certainly only forming stars out of hydrogen, but galaxies today are still using hydrogen for star formation. And we can use things like the O3 line to actually trace ionization on galaxy scales. So we can look at, for instance, spectroscopy of a galaxy, whether spatially resolved or integrated over the entire galaxy, and we can use the O3 line to tell us how much ionization is occurring. There are ionized species that we care about in the CGM as well. So when we're doing spectroscopy of the CGM, generally through absorption probes with a bright background source behind it, again, that's getting a little far afield, so I won't get into detail there. But we have other chemical species that we look for that trace ionization. So we absolutely think that ionization can change the chemical composition of the galaxies. The reason we use metallicity instead of being very specific about the chemical composition, and we generally kind of assume solar-like yields, or like the proportion of the elements are generally solar-like, that's what we assume, is because otherwise it gets really, really complicated. These are huge systems. I mean, this is not like a test tube where we can say like, oh, it's this percent, whatever. Right? So we're always thinking about things in terms of the metal fraction compared to the hydrogen fraction. That's what we're usually talking about when we're talking about composition. Now, the yields of different elements, the empirical yields of different elements in different galaxies can tell us things about the formation history of those galaxies, but generally speaking, when we're talking about composition, we're talking about metallicity as just this kind of like generic term. And what that means is we don't think that the ionization has a huge impact on chemistry the way we tend to, where we're glossing over these details. But for individual galaxies that we're studying in detail, that's where you start to care about how ionized is this galaxy. What is the fraction of gas that is ionized, for instance? And certainly we care about ionization for the impact it has on immediate gas clouds. So it's...
Well, I'm pretty sure that, like ionizing these galaxies or heating them up, or these mergers of galaxies can definitely create new chemical elements or substances. Definitely. Or...
I'll leave that to the people who study nucleosynthesis. I won't comment. It's very complicated, all of the nucleosynthetic processes. We think that we've nailed down where most elements come from. Up to iron, we can form them in stars, and then you have what we call R process and S process elements that can form in other ways, or can be released in other ways. For instance, binary neutron star mergers, which we saw with gravitational wave source 170817, GW 170817. We actually saw that we have very heavy elements, platinum, gold, etc., that are formed from these binary neutron star mergers. And there are obviously people who work much more on that, so I won't touch the nucleosynthesis side of things, except to say that no, we have a good handle on where stuff is coming from, and when we're talking about ionization, all we're doing is ionizing the individual chemical species that is already there. So we're not forming anything new with it, and with mergers, we're thinking on a very macro scale with these mergers. So we're not like merging, we're not creating fusion. I mean, I guess sometimes we promote star formation, which creates fusion, but we're not creating fusion on like the scale of galaxies where we can fundamentally create new elements, for instance. So no, the chemistry is mostly unchanged. It's just, again, I'll leave the nucleosynthesis to the nucleosynthesis people. Um,
I mean, it's
but we
definitely.
have a fairly good sense of, yeah, the chemistry kind of broadly of these things. Again, the chemists would totally get mad about it, but
I mean, it's definitely interesting to think about. I mean, maybe like a billion years down the lane, there'll be like a merger of two phenomena in our universe and create a completely different element that we've never thought of. And then in the end of your discussion, I think you were talking about how understanding these galaxies can tell us more about where we came from, kind of. And when I actually was talking to Dr. Sean Carroll at my expanse talk in I think in December, he was talking more about how in our universe we have so much entropy, and it's so interesting to think about that in such a disorganized universe, us humans, like an organized like phenomena, like came to be in the universe. And I think galaxies can really help us into diving deeper into this whole phenomenon of us coming into the universe. So I think we are running about a little bit on time. I really want to talk about low metallicity and its impacts on galaxy evolution. And I feel like we already talked about low mass, low metallicity galaxies. So I think we can go straight to our fourth topic, which was how we can use uh, observational and observational techniques and how we put that into more like theoretical modeling, because I know you guys have like immense amount of observational data, but then how do you put that into theoretical modeling and simulations? So I think it's very interesting to understand, because we can't really see the activity that happens in our universe in real time. So we use these data and theories that we have, and we try to put them into simulations to try to understand or predict the behavior of galaxies or anything or any phenomenon in our universe. So I really want to understand how you guys bring all those immense amount of observational data, because obviously there's so many missions that are happening. The Hubble obviously was one of the biggest missions, and then James Webb Telescope is also doing immense amount of work towards galaxies. So I just wanted to know a little bit about your perspective or your work and how you bring in theoretical modeling and observational data. Thank you for reaching part one of the podcast with Ava Polzin. In the next part, we'll be looking into her journey of astrophysics and how she got to where she is today, and a little bit about how her and her team managed the observational data to look into new perspectives about low dwarf galaxies, which we know so little about. Hope to see you guys in the